Okay. And so we got to the final mechanisms of regulating enzymes. We left off talking about how enzymes can be regulated. In other words, how enzymes can be turned on and turned off. And just to kind of reiterate, just go back here just a little and speak about or summarize these. We said one way was that there was allosteric regulation. So there were two sites on the enzyme being regulated. One bound the modulator, which is essentially kind of the key, if you will, that turns the enzyme on and turns the enzyme off. And then there's another site that actually binds the substrate. So this is one way to regulate an enzyme. The second one was slightly more complex. This was covalent regulation. And this was essentially a third-party enzyme that would add a chemical group, usually a phosphate, to the enzyme, and that would change the state of the enzyme, either turn it on or turn it off. And then there would be an opposing third-party enzyme, in this case, enzyme B, that would remove that chemical group and that would do the alternative function. So either turn it on or turn it off, depending on the specific examples. And we talked about protein kinase and phosphatases being example of those two types of third-party enzymes that help to regulate some of our other enzymes. And again, we'll point out many more examples as we go through each of the systems. The third mechanism of regulating enzyme activity is called feedback inhibition. And this is essentially where the rate of one enzyme is, the weight of some enzymes are constant, and then the weight of a specific enzyme is what determines the concentration of a product downstream in this reaction. And so essentially, the rate limiting step would be the use of that enzyme. So let me say that in another way. So we've got this flow of reactions here. Substrate A creates product B, substrate B creates product C, substrate C here creates product B here, product D here. And so what we see is that enzyme 2 and the conversion of substrate B to product C is the rate limiting step. In other words, this is the regulatory step of this series of equations or series of reactions. What that means is that enzyme 2 is influenced by the concentration of substrate or product C in this reaction. So if there's a lot of C being made, that is an indicator, or that will create the response that turns down or decreases the activity of enzyme 2. And that would be facilitating the slowing down or decreasing the amount of product C that's being produced, okay? And so this is one example of regulating the enzyme's activity, is that if there's too much product being created, the excess product will essentially turn the enzyme off, or at least slow down its activity in an effect or in a way to decrease the amount of that product that is being built up. Another example of feedback inhibition here is that we have product D influencing the rate of enzyme 1. So in this example, enzyme 1 is the rate limiting reaction here, or conversion from A to B is the rate limiting or the regulatory step. And so if there's a lot of product D being created, that would be a negative or a decrease in the activity of enzyme 1. And so that will slow the production of all of the substrates downstream and will eventually slow the production of a product D altogether. And so this feedback inhibition is a way to prevent excess products from being released, also a way to kind of regulate the enzyme. If it's making too many, if it's allowing the reactions to proceed too quickly such that the product is building up, we want to be able to turn that off or to regulate that, or to turn that down or decrease the activity. And then the fourth example of this, which is a lot more rare, feedback inhibition is by far the more common mechanism, but feedforward is kind of the opposite of what we see with feedback. And so essentially this substrate B, which is upstream in the series of these reactions, if there's a lot of substrate B being created, or a little bit rather, excuse me, a little bit of substrate B being created, that is an indicator to increase the activity of enzyme 3, which is downstream in the series of this reaction, okay? And so that would be kind of turning up the enzyme's activity or the enzyme's catalytic rate, and that would be allowing it to produce more of product D by using up more of product B or giving us more of product D at the end. Okay, so this is basically feeding forward or feeding upstream in the series of reactions versus feedback inhibition, which is feeding backward or regulating an enzyme that was downstream in the membrane, in the reaction. Okay. All right, I'm going to pause and see what questions we have, and then we're going to look at a few practice questions, and then we will move on to cellular respiration.
So you said feedback, feed forward is rare, but like when does it actually happen? What situation?
So I can't really think of examples off the top of my head, but it's very rare. It's kind of like positive feedback. And essentially, it's just the opposite direction of regulation. So instead of regulating something that's previous to the substrate or product that's being, that's influencing the enzyme, it's regulating an enzyme that's ahead. Okay, so if there's a product B being built up or too little, either way, we can influence the state of an enzyme that's ahead in order to either increase how much of that product can be used up or to decrease or slow down the enzyme if it's not being created fast enough. So it's just the opposite direction. I honestly can't think of any examples off the top of my head. That's probably just how rare it is in terms of our physiology.
Okay, sounds good. Thank you.
Sure, no problem. Okay, any other questions? So that was a really good question. Okay, so I'm going to go ahead and launch this poll here and we'll look at a few practice questions. Okay, let's take a look here. So the question is, if the activation energy of a reaction is high, then the rate of the reaction is, a lot of you selected B, and B is correct, okay? If the activation energy of the reaction is high, then the rate of the reaction is going to be low or slow, right? It's going to proceed very slowly because it's going to need more energy in order to allow that reaction to proceed, okay? If the activation energy of the reaction is low, which is what an enzyme does, it lowers that activation energy, then the rate or how fast the reaction can proceed is going to be high. Okay, so the answer here was B. Let's look at another one. Okay, last few seconds here. So an enzyme changes only the rate at which a reaction occurs. This catalytic rate of the enzyme is dependent on all of the following except. All right, a lot of you selected D. Okay, D is not correct, but let's see why. There was an even split between A and B. So essentially, we're looking at the catalytic rate. And remember, we said the catalytic rate was how fast the enzyme is producing product per unit time. And so we talked about 3 ways that that can increase. If the substrate concentration increases, more substrate to work with, then the catalytic rate will also increase. If the enzyme concentration increases, more enzyme around to actually proceed the reaction, then the catalytic rate will also increase. We also said that D was a part of one of the factors of increasing the catalytic rate. If the affinity for the enzyme and substrate increases, in other words, if they're more attracted or affiliated to each other, then the catalytic rate will increase as well. The activation energy does not determine the catalytic rate. Rather, the catalytic rate will then influence the change in the activation energy. So it's not correct to say that the catalytic rate is dependent upon the activation energy, okay? So the correct answer here should have been A, okay? This is not a factor that influences the catalytic rate. Okay, the other 3 factors do.